Hello and welcome to this course on electromagnetic fields and waves. Electromagnetics is a cornerstone of electrical engineering, physics, and communication systems. It describes how electric and magnetic fields are produced, how they interact with matter, and how they give rise to electromagnetic waves that power modern technologies, from electrical machines to wireless communication and medical imaging. In this course, we divide our learning into two modules. Module 1 will focus on vector analysis and fundamental laws. We will cover gradient, divergence, curl, theorems of vector calculus, and the classical laws such as Ampere's and Faraday's. Module 2 will focus on fields and currents. We will explore electrostatic fields due to charges, magnetic fields around conductors, time-varying fields, and the important concept of conduction and displacement currents. By the end of this course, you will have a solid foundation in electromagnetic field theory, preparing you for advanced studies in wave propagation, antennas, and modern communication systems. Module 1, Vector Analysis and Fundamental Laws. 1.1 Introduction to Vector Analysis. Electromagnetics relies heavily on vector mathematics. Fields such as the electric field and magnetic field are vector quantities. They have both magnitude and direction. To describe how these fields behave in space, we use mathematical tools from vector calculus. Three operations are particularly important: gradient, divergence, and curl. 1.2 Gradient. The gradient of a scalar function describes the rate and direction of maximum increase of that function. If we think of temperature in a room as a scalar field, the gradient points toward the direction in which the temperature rises most rapidly. In electromagnetics, the gradient is used in defining the electric field as the spatial rate of change of electric potential. 1.3 Divergence. Divergence measures how much a vector field spreads out from a point. Imagine water flowing from a sprinkler. At the nozzle, water diverges outward. In electromagnetics, divergence is important because it relates to the concept of charge density. Electric charges act as sources or sinks of electric fields. 1.4 Curl. Curl measures the tendency of a field to rotate around a point. Imagine placing a tiny paddle wheel in a fluid flow. If the wheel spins, the field has curl at that point. In electromagnetics, curl is fundamental in describing how magnetic fields are generated by currents and how changing electric fields create magnetic effects. 1.5 Integral theorems, Stokes and Gauss. Vector calculus also provides integral theorems that connect surface and volume integrals with line integrals. Stokes' theorem relates the circulation of a vector field around a closed path to the curl of that field over the surface it encloses. This theorem is key in understanding Faraday's law of electromagnetic induction. Gauss' theorem, also known as the divergence theorem, connects the flux of a vector field through a closed surface to the divergence of that field within the volume. This theorem underlies Gauss' law for electricity, which connects electric flux to enclosed charge. 1.6 Ampere's circuital law. Ampere's circuital law establishes a relationship between electric currents and the magnetic fields they produce. The law states that the circulation of the magnetic field around a closed path is proportional to the total current enclosed by the path. This principle is the foundation for understanding how current-carrying conductors generate magnetic fields, and it paved the way for modern electromagnetism. 1.7 Faraday's law of electromagnetic induction. Faraday's law describes how a time-varying magnetic field induces an electric field. This phenomenon is the basis for electric generators, transformers, and inductors. According to Faraday, the induced voltage in a closed circuit is proportional to the rate of change of magnetic flux through the circuit. This law bridges electricity and magnetism and is a cornerstone of modern power engineering. Module 1 Summary. In this first module, we build the mathematical and conceptual foundation for electromagnetics. We introduce gradient, divergence, and curl as tools for describing fields, reviewed Stokes and Gauss theorems as bridges between integral and differential forms, and discussed Ampere's circuital law and Faraday's law as fundamental principles. These tools and laws set the stage for analyzing actual electric and magnetic fields in space and time.